For most of human history, our problem with astronomy was the same problem we have always had with exploration. We could not see far enough. We needed bigger mirrors, more sensitive detectors, higher orbits. The bottleneck was always the telescope. We built better ones, and we saw further. And that was how science worked for 400 years. That era is over. Right now, a spacecraft called TESS is watching 2.2 million stars simultaneously, continuously measuring the faint flicker of their light with a precision that would have been unimaginable a generation ago. In 7 years of operation, it has generated more data about the night sky than all of the world's ground-based observatories combined have produced in the history of astronomy. It has already confirmed hundreds of exoplanets, worlds orbiting other stars. But here's the thing that changes everything. Buried in that data, unread and unconfirmed, are thousands of signals that nobody has ever properly examined. Real planets, orbiting real stars, their signatures sitting in an archive on a server somewhere. Not because the telescope missed them, because we ran out of human beings fast enough to check. Earlier this year, an artificial intelligence system called Raven went through just the first 4 years of test data and found more than 100 planets that had been hiding there all along, including 31 that had never been identified by anyone. And it flagged over 2,000 more that are still waiting to be confirmed. This is not a story about an AI finding some extra planets. This is the story of the moment when science outgrew the human brain, and what that means for the search for life beyond Earth. TESS, the Transiting Exoplanet Survey Satellite, launched in 2018 and works by watching for the tiny dimming of starlight that happens when a planet passes in front of its star. The technique is called the transit method, and TESS executes it on a scale that is genuinely difficult to comprehend. 4 cameras, 2.2 million stars, continuous observation, sector by sector, across the entire sky. By the time Raven was pointed at the archive, TESS had confirmed roughly 700 exoplanets through its primary pipeline. That sounds reasonable, until you understand what that number is actually telling you. TESS had flagged tens of thousands of candidate signals over those same years. The gap between signals detected and planets confirmed was not a scientific gap. It was a labor gap. Every candidate requires individual analysis, ruling out false positives from eclipsing binary stars, from background contamination, from instrumental artifacts that can look convincingly like a transiting planet if you are not careful. Human researchers were working through the backlog as fast as they could, and the backlog kept growing. This is the new shape of science in the 21st century. The bottleneck is no longer the telescope. We have already crossed the threshold where our instruments can collect data faster than our civilization can understand it. Missions like TESS, like Gaia, like the future Vera Rubin Observatory, are designed to observe the sky at a rate that assumes AI processing will exist to handle the output. The data is already there. The planets are already detected. What is missing is the computational power, and increasingly, the software, to confirm what the telescope has already seen. Raven was built specifically to close that gap, and what it found in 4 years of overlooked data suggests the gap is far larger than anyone had publicly acknowledged. When the team at the University of Warwick finally pointed Raven at the TESS archive, they were not expecting a revolution. They were expecting efficiency, a faster way to process a backlog that was already years deep. What they got instead was this: 118 confirmed exoplanets. 31 of them were brand new worlds, never identified in any catalog, never flagged by any previous analysis, sitting in data that had been collected years earlier and simply never properly read. And beyond the confirmed planets, Raven flagged over 2,000 additional high-quality candidates, nearly 1,000 of them entirely new, all of them waiting now for follow-up observations that will determine whether they are real. So how did a software system find planets that years of human analysis had missed? The answer is not that Raven is smarter than a scientist. The answer is that it does not get tired. It does not get bored. It does not unconsciously apply the shortcuts that any researcher develops after spending 10,000 hours looking at the same type of data. And in a catalog of 2.2 million stars, those shortcuts, the small, invisible decisions that happen when a human being is working through a long list of candidates after a long day, are precisely where planets go to disappear. The specific problem Raven was built to solve is called the false positive problem. When a planet passes in front of its star from our perspective, it blocks a tiny fraction of the starlight, and the star dims briefly. But dozens of other phenomena can produce the exact same dimming pattern: an eclipsing binary star in the background, a grazing stellar companion, an instrumental artifact in the camera readout. Human researchers learn to distinguish these cases through experience, and that experience introduces bias. Raven was trained on hundreds of thousands of synthetic examples of both real transits and false positives, and it applies the same full statistical test to every single candidate, every single time, without exception. No shortcuts, no fatigue, no unconscious filtering. The result was that signals which had survived the automated detection pipeline, but been quietly deprioritized by human reviewers, signals that were real, that represented actual planets, were caught, validated, and added to the confirmed catalog for the first time. So why had those 31 planets been sitting in the archive undetected for years? The answer reveals something important about how modern science works when the data becomes too large for humans to fully process. Some of the signals were simply too ambiguous to prioritize. Not obvious enough to fast-track, not suspicious enough to dismiss, they drifted into the middle of a queue and stayed there. Raven does not have a queue. It examines every candidate with the same level of scrutiny. Others looked too much like false positives. A nearby star, background contamination, or an instrumental artifact made the signal appear suspicious enough that human reviewers moved on to more promising targets. Raven didn't. It checked anyway. And in some cases, those overlooked signals turned out to be real planets. Among the newly confirmed worlds were planets orbiting their stars in less than 24 hours, completing an entire year in a single Earth day. Others were found at the edges of the Neptunian desert, a region where Neptune-sized planets should be common but are mysteriously rare. Something is removing them. We still do not know what. But the most important discoveries may be the least dramatic. Some of these planets belong to multi-planet systems, suggesting there could be additional worlds farther out. Worlds TESS could not easily confirm because their orbits are too long. Potentially habitable worlds. Every planet Raven validates is a new door, and what lies behind those doors is the question driving this entire story. Here is the part that almost no coverage of Raven has addressed directly. The team analyzed the first 4 years of TESS data. TESS has now been operating for 8 years. If the results scale even roughly linearly, there may be hundreds more confirmed exoplanets waiting in data that already exists. The satellite does not need to point at another star. The photons have already been collected. They are sitting in files on servers right now, waiting for a system smart enough to read them. This is becoming the defining pattern of 21st century astronomy. Years after Kepler shut down, astronomers are still finding planets hidden in its archived observations. Worlds that were there all along, invisible to the tools available at the time. TESS is producing data even faster. The backlog is growing faster than it can be cleared. And this is where the story connects directly to the search for life. JWST can analyze the atmospheres of selected exoplanets, searching for water vapor, carbon dioxide, methane, and potentially biosignatures. But it cannot examine every world. The planets it studies come from confirmed exoplanet catalogs. Every planet Raven validates becomes another candidate for follow-up. Every new world recovered from the TESS archive improves the list of targets that missions like JWST and eventually the Habitable Worlds Observatory will use in the search for life beyond Earth. The Warwick team has made both their pipeline and candidate list publicly available. What began as a computational project at one university is now an invitation to the entire astronomical community. We are not waiting for the telescope to discover something new. We are processing what it has already found. And the answer to the oldest question in human history may already be sitting in the archive. There is a practical lesson in Raven's results that extends far beyond exoplanet catalogs. The search for habitable worlds is not purely academic. It is target selection. Decisions about which planets JWST studies and which systems future missions prioritize are being made from an incomplete map of the sky. As Raven demonstrated, that map already contains confirmed planets nobody realized were there. For missions that cost billions of dollars and take decades to build, systematic gaps in that catalog are not a minor inconvenience. They are a real operational risk. Every new planet added to the record improves every decision that follows. The 31 newly confirmed planets had gone entirely unnoticed. They were absent from every catalog not because TESS failed to observe them, but because no tool sensitive enough had been applied to the data. How many of the remaining candidates are in the same position? What this means for long-term exploration is simple. The map we use to plan humanity's next steps is incomplete. It always has been. But for the first time, we have tools capable of narrowing the gap between what our telescopes have observed and what our science has confirmed. And that matters. Raven's confirmed catalog is now public. Every one of the 118 validated planets, every one of the 2,170 flagged candidates, is available to researchers worldwide. Right now, observatories on 6 continents are beginning follow-up programs to examine the most promising of those candidates with ground-based spectrographs and photometers. Some of those follow-up observations will rule out false positives. Others will confirm new worlds, adding them to the permanent scientific record. And at some point in this process, it may already have happened, the data may already exist in someone's observation queue, a planet will be confirmed that sits in the habitable zone of a nearby sun-like star, at the right distance for liquid water, the right size for a rocky surface, the right orbital period to suggest stability. JWST will be pointed at it. It will examine the starlight filtering through that planet's atmosphere during transit, and it will either find something or it will not. The point is not that we will definitely find life. The point is that for the first time in history, the data that would tell us one way or the other almost certainly already exists, somewhere in the archive, in a file that Raven has already flagged, waiting for a follow-up observation that is already scheduled. We are not searching blindly anymore. We are reading a document that has already been written. We are just still learning the language. TESS is still operating. The archive is still growing. Raven is still running. And somewhere in 2.2 million stars, in the light that has already been collected, recorded, and stored, the answer to the question humanity has been asking since the first night someone looked up and wondered if anyone was looking back, that answer is waiting. We are not waiting for the telescope to look in the right direction. We are waiting for the machine to finish reading what the telescope has already seen.